again. Let me introduce myself and talk about the thing I wanted to bring to you. It's my first English talk, because I talked a lot in Russian but not in English, and I hope it will be fine. Let's talk about programming languages. And I'll keep speaking as long as we lost. Okay, everything is started now, finally. I will not talk a lot about me as long as I took time from now. So let's talk about programming languages. From the very beginning, from the very start of their, it was creating for every programming language was serving its own purpose. It was growing with its own approach. A great example: Erlang that was created for telecom was able to do majestic things. It to reload its own code parts without. So you just change the code, deployed it, was restarted. Because you're working with telecom, you always have something chatting, and you do not want to hesitate these people. You do not want to break the connection. And that's why Erlang was created. But it doesn't have some strings for a very, very long time, because telecom didn't need it. Programming started with math problems, and it was developing with mathematicians who wanted to abstract from bare metal and assembly, moving to formulas. It was a narrow fortran. Sometime later, around 60s or 70s, depending on country. I'm from Russia, so it was late for me, so I don't know about other countries. Because socialism, business started to utilize programming heavily for their needs, and object-oriented programming emerged, manipulating physical world objects like in warehouse. So you pick up the cargo, place it in another place, and you create an object for that. Java was essence of this approach, and still is. However, much of business and IT processes started in the 90s, and right now it's on its peak, and it will grow even more, because business processes to have strict algorithms, workflows, apply theorems to people and cash flows. That means that if you have a real business, you have a bank. I'm speaking about bank because I'm from bank. You have to do the strict code, because if you miss something a little bit, you lose the money. So guarantees of code working is equal to guarantees of money not losing. These codes emerge of functional and object-oriented programming approaches. Popular object-oriented programming brings functional elements to them to survive, and functional programming is bringing in object-oriented programming elements, but it's in its own matter. TypeScript is which is a popular superset of JavaScript that brings type system, is one of the most popular programming languages nowadays, and in this autumn it made few important steps that change a lot. It looks not a lot, but actually it changes everything. What is even more important that there is a thing called formal verification systems. It's Lean, Idris, Coq, and they are gaining popularity. They were hard and complex in days before, but now they're way simpler. That's how the code in Coq looks like. It's not very hard, it's not very simple, it's something between C and Erlang and Haskell, but you can read it. And when you wanted to do something that is formally verified 20 years ago, we had to do some crazy stuff, and now it's just another programming language that forces you to write strong things. Why I'm talking about it? Because let me give you some crazy example. If you worked with TypeScript, if you worked with TypeScript types, you know that it's quite hard sometimes to implement what you want. But now you can do crazy stuff like that. You can pass a string as generic argument, and you will have a verification in compile time, not in runtime. So you just type it in your own IDE, and it's just saying, okay, you cannot write that. I've parsed the string, and it's not valid. Not in dry time, not in browser or Node.js. It's checked in type system like it was in Scala during compilation or something else. So how does it happen? This part is fun. It requires also a bit of math, but it's fun. There's a thing called Greenspoon stance rule. It tells us that any complicated program written in any programming language will have ad hoc, informally specified, bug-hidden, slow implementation of half of Common Lisp. Common Lisp is a programming language from 80s or 70s that was purely functional. It was quite simple, and it was from a group of languages that was as simple as possible, and you can implement them in in a few days when you started to work with new platform. And it was so simple that some special physical machines, physical stands with Lisp interpreter were made in the 80s. But why is it important? Because there is also another thing that is called halting problem. Halting problem is a problem from 20th century that was proved that it's not possible to solve it in every possible programming pair input. So it means that if you have a program, you cannot tell whether it will finish or not in expected time. You cannot tell whether it will finish or not at all, because to understand it, you have to spend that enough time as this program will require you to. Because if you have an algorithm that passes for 20 years, it's you have to wait 20 years because the thing that is running around this code will take all the same time. And this 1 plus 2 means that when you combine it, it means that TypeScript is complex enough to become Turing complete. Is it Turing complete? Yes. In 2017, there was discovered that TypeScript is Turing complete. It means that it can hang. If it will hang, it will just stop working and it will break the stuff. So in 2017, just okay, let's make kill switch. We have depth of 52 or something like that. Stop checking the types and you're making something very complex. You're making something extremely complex doing it. But in 4.1, some constraints that were bundled were removed. The most important blocker removed was, but let's talk more about Turing complete. There is a special list called accidental Turing complete. So just understand, you can accidentally make something Turing complete. There is C++ templates or preprocessor, and it's fine. You just expect this from this. Okay, HTML5 and CSS3. Okay, you do this, but it's program. You're making logic in recursive manner, and it works somehow. So you can create you can't create Game of Life 2D, but you can probably create you can create Game of Life in 3D that will work for like a few hours. It's not that good, but it will warm up your computer and then accidentally stop because you didn't declare enough variables. But it will work for a while, so it's rather Turing complete. But things getting weirder. And okay, SQL, I understand. x86 MMU, it's a subset of instructions for x86 processors, and it's quite crazy that you have just math operations there, like multiplication, subtraction, etc., etc. They're complex, but they're generally just processing data, and accidentally it's Turing complete. But you know what's weird? Sendmail. You can write sendmail instructions and just make them hang. But let's dive deeper. Pokemon Yellow is Turing complete. You can write programs in Pokemon Yellow just by placing elements. Okay, let's go to the physical world. Magic the Gathering is Turing complete. You can just combine the cards and they will make it Turing complete. Okay, I have more fun examples like Portal and Computer and Point, but you get the point. Let's move further for hard part. TypeScript in its own, about how to use the Turing completeness of TypeScript, the glory of your own push. So what happened in TypeScript 4.0 at all? You have list of types, key remapping, recursive conditional types, so that's it. and some other stuff that you don't need. You need here only template literal to parse the strings and recursive types to make recursion. Also, there was variadic tuplet types in back in 4.0, and it was able to compact this kind of declaration into this one. It's way simpler. It's way easier to do, and it allows you to not getting stuck into crazy things. What is examples of work with strings in TypeScript 4.1? You can just declare that you want to use this kind of annotation. It's easy. It's comfortable. It's easy. It seems sane. You can do like something like that. So yeah, okay. We have now a string interpolation is in types of TypeScript. So you can combine the things. You can do even something like that. So it's like quantity, color, and you combine it all. It's great feature specifically for React and Redux developers because most of teams are using prefixes and they had to declare prefixes manually or they had to create some generation codes. But now they can just use declarations of prefixes and makes lives easier. It's really great functionality, and it can be utilized to handle the strings, to parse JSON in the end, as you can understand. But the most interesting thing it's not key remapping, it's recursive types. What does it mean? Reference a type in its own if you're using condition, because otherwise you're getting an infinite loop. So you have to use a condition, and now you can implement something like deep flatten. So you're just casting any depth data to number. It's simple, it's easy, and it's great looking, actually. So coming back to Lisp, some people are saying, okay, you like Greenspan, okay, you can accidentally create a Lisp. So let's create a Lisp intentionally. So simple Lisp, the core Lisp is requiring you only like 6 or 7 things to implement. It's thing called atom. It's like variable. It's containing any value. So for some implementations, numbers are enough, or strings are enough, or objects are enough, or just pointers and hex numbers. You need equality. You need a list constructor. It's called cons in Lisp because it's not actually a list itself. It's like you have a tuple of 2 elements, first element and second, and the second one, if you need to add the third element, you just pick these 2 elements, place it here, and add the third one here. So you have an array of 1, then a block of 2 and 3. So it's like nested array of 2. So for us, we will be using a list that is way simpler structure, and it will not break the mind. You need head and tail functions, and you need a way to declare the lambda. So it's really simple. Here you need to bring the cons, the lists. Head and tail are a bit more complex, but you have to do this because, okay, you have to infer the first element and the spread elements of your list to processes. It's not that hard, it's not that complex. It's just a new functionality that was brought a few verses ago, and you may not know, but if you're using infer, that means that you're making some kind of pattern matching, you're bringing the structure to check against, and if it's matching, you're just extracting the value. So you can extract the value from promise with infer or from array with infer, and it's perfectly fine, and it's great functionality to use. And you have a lambda, but you cannot create interface programmatically. You cannot create interface in another interface. It's not working like that. So there is a thing called lightweight HKT, high counted types that allow you to pass arguments to another arguments, and it's implemented in some of that matter. You can check the FPTS library to verify whether it's working or not. You have to implement a few things. So actually, the core thing is that you're implementing URI2kind. You're implementing the structure that is empty from core. Then you're just declaring URI2kind array is array. URI2kind of something else is something else. For example, You're bringing year to kind object, and you're bringing its generic inside. So you're just passing the generics of year to kind inside its own construction. It's a trick. It allows you to implement some simple high-order functions, but you're limited to one global list of these functions, so you cannot declare some local-level variables. Also, there is one more thing you need to understand. There is two types that are never and unknown. They're rather new. They appeared like 2 years ago or 1 year ago, and they are a bit more complex than any that was used for quite a while. So the difference between them is that when you're using never, when you're combining never with something else, never disappears, because if you have never or two, you're getting two. If you're getting never and two, it's obviously comes to never, because if you're combining never with something, if you're joining never with something, it's still never. Like come to my house at Friday or never, or come to my house at Friday and never. No, it's not a bad example, but you get the point. And unknown, it's like, okay, I do not know what I'm handling. It's like a bag. I don't know what's in bag, but I have this bag. And if I'm checking the shape and it matches like, I don't know, square, it's square inside. But if it's square or something unknown, it's unknown. It's important to combine this never and unknown with ternary expressions, with conditional expressions in TypeScript, because they gain a lot of functionality from that. So this is a simple example of how to use this mapf. You're bringing year to kind here, and actually TypeScript at this moment is getting to look like a lot like common JavaScript. So let's enlarge a bit. Oh no, it's not enlarging, sorry. So here you're just doing the tail recursion, just like in some JavaScript code. Not everyone is writing like that, but in TypeScript we have to write like that. So it's perfectly fine, and you're just doing, okay, if I have a head, then I'll spread head and tail, and I'll map the tail. Or if I don't have a head, I'll just return empty array. It's totally mapping to JavaScript. It's totally mapping to any functional language, and it's way more simpler than it can look like. So how can we use it? For example, simplify. If you want to compare two arrays and check out which one is longer, you're just checking whether each first one extends the second one. So like you have an array that's you have to map this arrays to make them array of unknown. So it's not number, it's unknown with using the type called G. Here, it's a short one for generic. It's just creating the unknown array. And if you're just checking, okay, if array 1 extends array 2, that means that it contains first 3 elements and something else. It's extending it. It means that it's a large array. Otherwise, it's not. So here is a simple example of compare. But how can we use it? We can use it like that, for example. We can use it not to compare, but to pick the longest array. We can pass array of arrays in TypeScript and just extract the type of longest array to pass it inside. So here we're using compare function, compare generic from previous slide. We're using an infer, we're using compare, and here we're just bringing the longest thing. It's looking weird, I agree. So here we have infer C that is spread. So we are comparing first 2 elements, and if first one is largest, we are picking it. Otherwise, we're picking the second element. That's how we are extracting it. Another thing is that if we have a last element, that means that actually we have, as long as infer C, infer spread sometimes causes empty arrays, that means that we've passed here only one element in longest, or here one element. It means that we're handling only empty array of one element, and thus we should return T. So it's kind of weird, I agree, but it's magic. It's TypeScript magic that you sometimes should use, but sometimes not. Coming back to the previous example, so we have an element type. It's example from documentation, from description of recursive types. Here we're extracting just a number, but what if we want to extract not just only number, but something even more? We want to flatten. It's not what I'm devising it to write. It's code from existing library that was working with previous versions. They were supporting the recursion, but they were not supporting it in general. They had a limit like 10 to dive inside. Now we can write like this. Simple, elegant, and readable. It's readable as hell comparing to previous types. Small note here, you don't have type iterable. It's just a combination of array, arguments list, readable array, unit array, etc., etc. So just generic iterable. I didn't spend the time to declare it, so just keep in mind that it's just some kind of generic iterable. You can use it whatever you want. So here we can extract not only common type, but we can extract the flatten of iterational types. As an example I like, by the way, this is simple conversion to JavaScript code, and you can see that types in TypeScript are really looking similar to JavaScript code, a lot of looking like JavaScript code, so you can really think about generics like an array, like functions, and like generics are their arguments and they are returning the values. Of course, they have parts like infer that are pattern matching, but not at all. Another example, my beloved one, I use it a lot because I use it in my own library, is like list. It's a zip function, so you're passing an object with arrays in keys. So you have A1, 2, B2, 3, 4, and you just want it to split into several objects. And this is simple as hell. So you're just iterating objects. You're just picking object head, and object head you're picking just first elements. In rest entail you're picking all the other stuff, and that's how you're getting it to work. Okay, so let's go to the hardest part. So this is the example I've shown in the very beginning. It's a parse-JSON structure. How it works. First of all, you need to understand how it works inside. I'll just explain it in brief. So you in inside it has a structure of two elements. First one is parse value. Second one is remaining string. To keep it in mind, because you cannot declare variable in types. You have to pass it always. You have to always pass the value, so it will work. That's why it's working like that. So if it's extending result, then it takes the first value from the result and return it. Otherwise, it's returning the result itself. It's an error. It's an error in that parser. But what is more interesting is the string info result. In info result, you can actually infer everything. You're not limiting it to infer in any manner, but you have to write ternary expressions. That's why there is never in the end, because that's how you're just defining the variable. You're defining parse-JSON result is parse-JSON value t. It's a clever construction. It's quite complicated, but it's nice. So what's inside parse-JSON value? It's looking complicated, and one of the most weird part here is when I was just researching this case was this string. String extends state, not state extends string. I was thinking this was a typo or mistake. No, it's not, because it turned out that when you're using a template string, you're expecting it to extend string, but not the string to expect it. So you're checking in that manner that it's not some generic string, but it's concrete string. And when you're trying to understand the rest of it, let's extend TypeScript syntax with something from functional world. And now it's looking way simpler. Now it's looking extremely simple. So you just understand that here it's just pattern matching. You're matching the pattern on string and extracting the value from it. So you just recursing. Another great thing here I like is eat whitespace. Eat whitespace is a special type that is just cropping the whitespace, like cropping whitespace and new line until it encounters something else to pass it to another functions. Other things here are also quite simple. I'm not saying it's simple to understand from now, but if you will find some kind of this code and spend a little bit of time, you'll finally understand that it's just switch case, switch case, switch case, just written in a strange manner. And also same for pass, just on array function declared here. And okay, okay, I was running. I hope you've understand a lot, you appreciate it a lot. So what I want to say to you, when you encounter this kind of complex code, when you encounter this kind of overcomplicated code, understand that sometimes it's working, sometimes it's making world better, sometimes it's making your type stronger and harder to protected, way more protected. But if you're writing this kind of code, remember that you're responsible for sanity of other people that will come to your pull requests and will try to understand it. Remember the feelings that you were experiencing when you were watching the slides, and I'm pretty sure that most of you were, okay, it's too hard, it's extremely hard to understand in some parts. Understand that when other people will come to you and see this code, they will ask the same question. They will get stuck. They will get, it will be hard for them. So you have great tools now. If you're using TypeScript, update to 4.1. It will probably not break anything, but bring more errors about typing because it became a bit stricter. Know that you have these kind of tools. Know that you can implement way more, extremely way more. But also remember that it will be hard for your friends and colleagues to understand it. Thank you. Thank you all. I hope you all appreciated it. I hope you all enjoyed it. I hope you all liked it, and thank you. Probably I should stop streaming, I think. Stop streaming. Or maybe someone else have a question, I'm willing to answer it. Okay. So, thank you everyone for watching again. If you have a questions, just type them in a chat. I'm reading the chat now. Well, I guess that's it. No questions inside, so probably I'll go. I need to ask. Strange camera. I tried it. New software that was recommended by Ox, and looks like it's messing with my own background. I didn't know why my background is switched back and forth. It's unexpected. Okay. Appreciated talk with you a lot. First, thanks. It's really nice to see it. Well, okay. I think I'll go now. It's 10 minutes till next talk, but looks like no one else have a question. So, really, thank you a lot. It was a bit nervous for me, but great.